Question number 1. Use the roster method to write the given set. The set of whole numbers less than 7. Remember, the whole numbers include 0 and then the counting numbers, but we only want the ones less than 7. So we can only go up to 6 in order to stay less than 7. So the set of whole numbers less than 7 consists of the elements 0, 1, 2, 3, 4, 5, and 6. Number 2. Use the roster method to write the given set. The set of natural numbers less than 5. Remember, the natural numbers are just the counting numbers. But we want to be less than 5, so we can only go up as high as 4. So the set of natural numbers less than 5 is a set containing the elements 1, 2, 3, and 4. Number 3. Write a word description of the set. And this set is a set containing 1, 3, 5, 7, 9, 11, 13, and 15. It looks like the counting numbers, except that we're skipping all the evens. So actually it looks as if if you're looking at the counting or natural numbers, it's only the odd ones. So I would choose odd natural numbers. And then we stop at 15. But the phrasing of the question says less than, so it would be less than 16. If we stop at 15, that means we are less than 16. So the answer is the set of odd natural numbers less than 16. Number 4. Determine whether the statement is true or false, and if it's false, give a reason. We've got the set containing 2, 3, 5, and that tilde, that squiggle, is equivalent. So the set containing 2, 3, and 5 is equivalent to the set containing 8, 31, and 20. The key to this problem is realizing that the definition of equivalent says that two sets are equivalent if they have the same number of elements. So all we need to do is count. If you count the set on the left, there are 3 elements. If you count the set on the right, there are 3 elements. So by definition, those two sets are equivalent. And they're equivalent because they have the same number of elements. Number 5. The following bar graph shows the average student debt in each graduating class from 2008 to 2015. Notice that the debt itself is on the vertical axis and the year is on the horizontal axis. It further says, use the information in the graph and the roster method to represent each of the following sets. In A, we want the set of years in which the average student debt was greater than 30,000. So if we draw a horizontal line at 30,000, we want the years represented by bars that exceed that 30,000 mark, and that would be the years 2013, 2014, and 2015. B says the set of years in which the average student debt was greater than 20,000 but less than 25,000. So if you draw horizontal lines at 20,000 and 25,000, you want the bars whose tops are between those two lines, and you can see there are only 2 of them. That's the year 2008 and 2009. And finally, C, the set of years in which the average student debt was less than 30,000 but greater than 25,000. So I'm going to draw a horizontal line at 30,000, a horizontal line at 25,000, and I'm looking for the years represented by the bars whose top is between those two lines, and I think you can easily see that there are 3 of them. Those are the bars for years 2010, 2011, and 2012. The following table, this is number 6, the following table shows the winning times in the Kentucky Derby from 2006 to 2015. Use the information in the table and the roster method to represent each of the following sets. First of all, the set of years in which the winning time was greater than 2 minutes and 3 seconds. If you scan those years with times, you can see there are only 3 of them. 2010 is at 204.45, 2014 is at 203.66, and 2015 is at 203.02. Those are the only 3 years where the winning time was greater than 2 minutes and 3 seconds. B, the the set of years in which the winning time was less than 2 minutes and 50 seconds, but greater than 2 minutes and 3 seconds. So you want to be above 2 minutes and 3 seconds, but below 2 minutes and 3.5 seconds. It's a very small range, and if you scan through there, there's only one year in which that happens, and that is the year 2015, which is 203.02. And finally, the year in which the winning time was the least of all the given times. Again, you have to scan through there, but it seems that there's only 2 entries that are even in the 201 range, and the smallest of those is the one at 201.36, and that corresponds to the year 2006. Number 7, find the cardinality of the following set. The set containing 3, 6, 9, 12, 15, ... all the way up to 402. Now this problem requires a little bit of background, and if you remember from our classroom discussion, you probably don't need this background, but in case you don't remember, let me provide it. First of all, the cardinality is just the number of elements in the set, so we're trying to count the number of elements in the set, and the background is, we talked about when you have a long list of numbers that you want to count, there's a certain pattern that's easy to count without having to literally go one by one, and that is if the numbers are consecutive. And just to take a simple example, if I tried to count how many numbers were in the set containing 2, 3, 4, and 5, the formula is take the largest minus the smallest and add 1. So if you take 5 minus 2 and add 1, you get 4, and if you look, there's 1, 2, 3, 4 elements. So that's how it works if they're consecutive. So you might say, well, what does that have to do with this problem? Because in this problem, they're not consecutive. And that's where the second thing came in. Occasionally, they'll give you a set that's not consecutive integers, but the elements are actually multiples of consecutive integers. And that's what happens here. And you can see it by noticing that every single element in that set divides by 3. And if you divide every element by 3, you'll see that you get 1, 2, 3, 4, 5, ... up 134. In other words, 3 divided by 3 is 1, 6 divided by 3 is 2, 9 divided by 3 is 3, 12 divided by 3 is 4, 15 divided by 3 is 5, and so on. 402 divided by 3 is 134. So you can count the elements in those sets using the formula because they're consecutive, but they're the same number of those as there were in the original set because all we did is divide by 3. We didn't throw any elements out. So the trick here is to notice that if you divide by 3, you get a set of consecutive integers, and now you can apply the formula largest minus smallest plus 1. That'd be 134 minus 1 plus 1, which is 134. So there are 134 elements in that consecutive integer set, but that means they're the exact same number of elements in the original set, so the answer is 134. Number 8. Find the complement of the set given that the universal set is a set containing 2, 3, 4, 5, 6, 7, 8, 9, and 10, and the set we're looking at is the set containing 4, 6, 8, and 9. We want the complement of that set. To find the complement, you take the elements of the original set and compare them to the elements in the universal set, and you cross out each element in the set and remove those from the universal set, and whatever's left is the complement of the set. And what's left here after you cross out 4, 6, 8, and 9 is 2, 3, 5, 7, and 10. So the set containing the elements 2, 3, 5, 7, and 10 is the complement of that original set containing 4, 6, 8, and 9. Number 9. Insert the symbol for is a subset of, or the symbol for is not a proper subset of, to make this a true statement. Remember, the sideways U with the bar under it is the symbol for subset, and the sideways U without the bar under it is the symbol for proper subset, and if you put a slash through it, that means not a proper subset. Also recall that the only difference between something being a subset of another set or a proper subset of another set is equality. Proper subset knocks out the equality part. Otherwise, they're the same. So all you really have to do is take the elements on the left, the A, B, C, and D, and see if you find them on the right, and you do. So that means that the set containing A, B, C, D is a subset of the set containing A, B, C, D, E, F, G. So the symbol that you're looking for is the subset symbol. Number 10. Let the universal set be the set containing P, Q, R, S, and T, and then you've got some other sets given. We want to find out if the statement F is a proper subset of D is true or false. So what you have to do is write them out. F is the set containing S and P. D is the set containing P, R, S, and T. And if you look, the S on the left appears on the set on the right, and the P from the left appears in the set on the right. So that means it is true. It would be a subset of or a proper subset of, because as long as you don't have equality, the answer will be the same either way. Similar problem. Universal set is a set containing P, Q, R, S, and T. And then you have some other sets, including D, which contains R, T, S, and P, and E, which contains P and Q. You want to find out if D complement is a proper subset of E. So we need to first find out what the complement of D is. And remember, the complement of a set are the elements that are in the universal set but not in the original set. So I first need to write out what D is. D is the set consisting of the elements R, T, S, and P. And comparing that to universal set, if I cross out all those elements, the R, the T, the S, and the P, I'm only left with the Q. So that means that D complement is the set containing only a Q. So I'm comparing D complement to E, and I want to know if D complement is a proper subset of E. So if I write out D complement, which is the set containing Q, and then write out E, which is P implies Q, and notice that there's a Q on the left that also is repeated on the right, that means that that statement is true. And since you don't have equality, it would be a proper subset. It would also be just a regular subset of. As long as you don't have equality, the difference between proper subset and regular subset really doesn't matter. 12. Find the number of subsets of the given set. This set contains the elements 2, 11, and 9. And when you're finding the number of subsets, all you need to do is count how many elements there are and use the formula that says a set with n elements has 2 to the power of n subsets. So you've got 3 elements, 2, 11, and 9. Count them, there are 3 of them. So you raise 2 to the third power. That's 2 times 2 times 2. On the calculator, you use the power button and you get 8. So that set of 3 elements has 8 subsets. Number 13, a delicatessen makes a roast beef on sourdough sandwich for which you can choose from 9 condiments. A, how many different types of roast beef on sourdough sandwiches can the delicatessen prepare? Now, once you relate this back to what we've been doing earlier, it's easy. You can think of each condiment as being an element of the set of all condiments, so it's really like asking how many subsets are there of a particular set. And we know the answer to that is a set that has n elements has 2 to the n subsets. Here there are 9 condiments, so that would be 2 to the power of 9. And 2 to the 9th is 512. And if you haven't practiced using the power button on your calculator, you need to do so. You put the base of 2 in, then you hit the X to the Y button, which is the power button, then you type in 9, and then you hit the equal sign, you'll get 512. If you haven't practiced that on this calculator, you need to do so. B part says, what is the minimum number of condiments a delicatessen must have available if it wishes to offer at least 2,000 different types of roast beef on sourdough sandwiches? We already know that 9 ingredients or condiments is not enough. That only takes you up to 512. So just keep raising the power until you pass 2,000. So since 2 to the 9th is only 512, we try 2 to the 10th. Turns out that's only 1,024. But when you bump it to 11, you get 2,048. So it would take 11 ingredients to bump you up to 2,000 or greater, so that you could say that you offer at least 2,000 different types of roast beef on sourdough sandwiches. So the answer is 11 condiments. 14. A restaurant provides a brunch where the omelets are individually prepared. Each guest is allowed to choose from 9 different ingredients. A student has been asked to form the following sets. Determine the number of elements a student should have in each set. And the A is, how many different types of omelets can the restaurant prepare? Well, this is extremely similar to problem number 13 because we're doing omelets instead of sandwiches, really the only difference, and you're doing the ingredients of the omelet rather than the condiments that go into the sandwich. These numbers are randomized. In this case, the 9 came up, which is the same as the 9 from the previous problem, and the 2000 came up, which is a randomized result, but it happens to be the same as for the last problem. So honestly, the answer will be exactly the same. If you're looking for the number of type of omelets, you take 2 to the power of how many elements there are. The ingredients are elements, so there are 9 of them. And if you take 2 to the 9th, you get 512. As I said, this is a randomized example, but it came up exactly with the same random numbers from problem 13, so it shouldn't surprise you that the answers will be the same. So the A part, the answer is 512. The B part says, what is the minimum number of ingredients that must be available if the restaurant wants to advertise that it offers over 2,000 different omelets? Again, it's an omelet instead of a sandwich, but the 2,000 stayed the same. So you start taking powers of 2. You know that 9 only takes you up to 512, so then you try 10. It takes you up to 1,024. Try 11. That finally surpasses 2,000. So you need at least 11 ingredients. I call them condiments here, but really ingredients to get you over the 2,000 different omelets. 15. Let the universal set be the set containing 1, 2, 3, 4, 5, 6, 7, and 8. And then you've got some other sets, and you want to find the complement of the union of A and B. So the first thing you probably want to do is just do the union of A and B and worry about the complement last. So A is a set containing 2, 4, and 6. B is the set containing 1, 2, 5, and 8, and the union just tosses everything together. So if anything is listed in either, it goes in the union. So there's a 1 up there, there's a 2 up there, there's a 4 up there, there's a 5 up there, there's a 6 up there, and there's an 8 up there. So the union is simply the set containing the elements 1, 2, 4, 5, 6, and 8. But that's not the final result. We want the complement of the union. The complement is everything that's not in the union. So you take the union we just found above and cross out everything in the universal set that was in the union. That means you cross out 1, 2, 4, 5, 6, and 8. If you look closely, that leaves a 3 and it leaves a 7. So the complement of the union of A and B is the set containing the elements 3 and 7. Number 16. Let the universal set be the set containing the elements 1, 2, 3, 4, 5, 6, 7, and 8, and they give us some other sets. And this time they want us to find the set that represents A intersected with the intersection of B and C. In other words, there are parentheses around the B intersects C, so they want us to do that first. And once we get that result, then we intersect it with A. So I would start off just by writing everything out explicitly using the roster method. A is a set containing 6, 2, and 8. B is a set containing 3, 8, 1, and 6. And C is a set containing 1, 5, and 7. The parentheses tell you to work inside of those first, so I want to find that intersection first. The intersection is the overlap. So I notice there's a 1 in both, and that's it. There's no other common element. So the intersection of those two sets is just a set containing 1. Now we want to intersect that with the set on the left, which is the set containing 6, 2, and 8. Well, there is no overlap. There's no 1 on the left, and there's no 6, 2, or 8 on the right. So the intersection of those two sets is the empty set. The symbol is the circle with the slash through it, or you could write the set with no elements inside, just the braces. But they asked you specifically, for purposes of this exercise, to type in the word empty in all caps. Capital E, capital M, capital P, capital T, capital Y. Enter that as your answer instead of the symbol for empty set. And the only reason you're doing that is because that's what they asked you to do. 17, the universal set is a set containing 4, 5, 6, 7, 8, 9, 10, and 11. They give you some other sets, and they want you to find this complex intersection and union. A union B is grouped together, and B intersects C complement is grouped together. So we want to do each of those separately before we finally do the intersection last. So I just write everything out. A is a set containing 5, 7, and 9. B is the set containing 4, 5, 8, and 11, and it actually appears in 2 places. And C is the set containing 4, 6, and 10, and there's actually a complement, so I'm just going to symbolically write the accent mark, which indicates I still have to take the complement of it, and I'll just make an extra step out of that. So taking an extra step, I'll get that eventually. Moving back to the left side, I want to do the union of the set containing 5, 7, and 9 and the set containing 4, 5, 8, and 11. Now remember, with union, if it gets listed in either place, it goes into the union. So you have a 5, you have a 7, you have a 9, you have a 4, you have an 8, and you have an 11. I put them in order, 4, 5, 7, 8, 9, 11, but they don't have to be in order. And then on the right side, as I said earlier, I still have to take the complement of C. So if C is a set containing 4, 6, and 10, the complement will be everything in the universal set. It doesn't include 4, 6, and 10. So I go up to U and mark out 4, 6, and 10. That leaves me with 5, 7, 8, 9, and 11. So the set containing 5, 7, 8, 9, and 11 is the complement of the set C. And I just keep working. I got one more set of parentheses, so I want to work inside of there. So I want to take that intersection, and intersection means overlap. And if I look at it, there are several. There's a 5 in both, an 8 in both, and an 11 in both. So the intersection is the set containing 5, 8, and 11. And finally, I want to intersect those 2 sets, the remaining 2 sets. So I look for overlap. And again, there's a 5, an 8, and 11. So the intersection of those 2 sets is the set containing 5, 8, and 11. Number 18. Draw a Venn diagram to show the set A intersect B complement. Now this is one of the problems where I think it's simple enough that if you just say out in words what it means, you can probably just grab the answer immediately. And here's what I would suggest. In the very simplest case, just read it out loud to yourself. I would read this as A intersect B complement is the elements of set A and that are not in set B. So you want the things that are inside of A but not inside of B, and you should be able to just look and see that it describes the upper left Venn diagram. Those are the values that are inside of the circle A, but not inside of B. Now, if you'd rather not try it that way, you can use Venn diagrams and shading to get the same results, and I'll do it that way as well. You start out with the Venn diagram. You take the set A. The interior of set A is representative of the set A. And then you want to take B complement. B complement are the things that are not inside of B. So I'm going to use diagonal lines there. I shaded everything inside the rectangle that's not inside the circle B. So absolutely everything outside of circle B gets shaded. And then the intersection is the overlap. So you want to look where the diagonal lines overlap the solid shading. And where the diagonal lines and the shading occur, again, is the area represented by the top left Venn diagram. So either way, you get the same answer. Number 19. Draw 2 Venn diagrams to determine whether the following expression is equal for all sets A and B. You start out with 2 expressions. You've got A intersected with B complement, and then you have A complement union with B. And just take them one at a time and draw a Venn diagram for them and see if they come out to be the same Venn diagram. So you start off A and B, overlapping circles. B complement is everything outside of B. This turns out to be the thing we just did, so it should be old hat. I used vertical lines this time. A is the set of things inside of circle A. And if I'm doing an intersection, I want the overlaps. I want the vertical lines and the diagonal lines. I want the region of the Venn diagram that have both the vertical lines and the diagonal lines. And as you can see, that's the area, the same area we found in problem 18, because that's exactly the same expression from problem 18. So if you move over to the right, you get A complement union B. A complement is everything outside the circle A. I use vertical lines, shade everything that's not in A. Then I do B, and I use horizontal lines, or maybe they're slightly diagonal, semi-horizontal lines, I guess. And you're doing union. If you're doing intersection, you'd need the overlap, but the union is anything that's in either one. So anything that got shaded with either vertical lines or horizontal lines or both goes in the union. So it's everything except the interior of A that's not in B. So the union is actually the complement of what you started out with. So they are not equal. In this particular case, the one on the left and the one on the right are complements of each other, but the question wasn't whether they're complements of each other. The question was, were they equal? And unless they shade exactly the same area, they are not equal. 20. Draw two Venn diagrams to determine whether the following expressions are equal for all sets A, B, and C. You've got two expressions that are a little more complicated. In fact, they involve three sets. So this time when you draw a Venn diagram, you've got to put sets A, B, and C. So you have to have three circles. And you start out pretty much as you always do. On the left, it says A intersect B. Well, that's just the overlap between A and B. So I use those diagonal lines to shade the overlap. And then you want to get C. Well, C is everything inside of circle C. So I sort of did diagonal lines in one direction for A intersect B, and I did diagonal lines in the other direction for the set C. And since we're doing intersection, we want the overlap. If you're looking for the overlap, you can see they only overlap, the two types of diagonal lines only overlap in the absolute center of that diagram, which I call a wedge shape, that wedge shape that includes being in all three circles. Then you move over to the right, approach it the same way, except this time you're taking the complement of a union. So I would deal with the union of the sets and do complement later. The union of A, B, and C is just shading anything in A, if it's in B, if it's in C, if it's in the overlap of A and B or A and C or all three. If it's in any of those three sets, it gets shaded. That's what union does. But remember, that's not the final result. We want to take the complement of that. So the complement would be everything else. That'd be the outside area, the ones I've shaded that are outside of all three circles. And as you can see, the Venn diagram on the left does not match the Venn diagram on the right, so those two are not equal. 21 defines the difference of two sets and then asks you to calculate a difference. I hope that you don't need the definition of the difference because we've talked about it, but they actually repeated the definition of the difference of two sets. In other words, the first three lines is just a repeat of the definition. But what they really want you to do is find the difference of B minus A, and all you have to do is look at the two sets, B and A, and you start out with the set on the left side of the minus sign. In this case, that's B, and then you look at the elements in set A, and if there are any commonalities, you cross them out. So if you write down B, that's the set containing 3, 4, 5, and 8, and then if you look in set A, it contains 2, 4, 6, 8. So if you see any of 3, 4, 8, 5, and 8 in set A, you cross it out. And what you do see is that there is a 4 and there is an 8 in A that were also in B. So you start out with B and then you cross out anything from A that was in B, and whatever you're left with is a difference. Obviously, if you said A minus B, you would start off with the set A and then cross out any commonality with B. So the difference of two sets, you start out with the set on the left, write it down, and then you cross out any commonality that it has with the set on the right side of the minus sign. 22. Let U be the universal set which consists of English, French, history, math, physics, chemistry, psychology, and drama, and then they've got several other sets, and they've asked us to find the union of B and C. Well, union means just throw them all in. You take everything in B, which is physics, English, French, chemistry, math, and then you add anything new from C. So that would throw in drama and psychology. French is in both, and so you already put that in once. You don't need to put it in twice. So the union of B and C is the set containing physics, English, French, chemistry, math, drama, and psychology. And the number of elements you simply count. you count 7 of them, so the number of elements in the union of B and C is 7. 23. Let the universal set be the same as before, the set of English, French, history, math, physics, chemistry, psychology, and drama, and they've given you some other sets. And this time they want you to find the number of elements in set A and add it to the number of elements in set B, and then add that to the number of elements in set C. So you just need to do the count. If you count A, you get 1, 2, 3, 4. If you count B, you get 1, 2, 3, 4, 5. If you count C, you get 1, 2, 3. So it's simply 4 plus 5 plus 3, which comes out to be 12. 25. Given the number of elements in set A is 1500, the number of elements in A union B is 2250, and the number of elements in A intersect B is 310, find the number of elements in B. Now, you can do the inclusion-exclusion principle, or you can just draw Venn diagrams and figure it out that way, and you probably can just play around with a little of both. But let's take a shot at it using the inclusion-exclusion principle. The inclusion-exclusion principle simply tells you that you can find the number of elements in the union of two sets by taking the number of elements in each set separately, in this case the number of elements in set A plus the number of elements in set B, and then you subtract off the number of elements in the intersection of the two sets. Why? Because if you count them in A and you count them in B, you double counted the ones that are in the intersection, so you've got to subtract off one of the double counts. So that's the inclusion-exclusion principle. And if you look at it that way, they give you all but one of the numbers. They tell you that the union number is 2250, the number in A is 1500, and the number in the intersection is 310. The only thing they don't tell you is how many is in the set B, which is what you want. So on the right, you can just take 1500 minus 310 and get 1190, and then subtract 1190 from both sides, and you'll find out that the unknown value, which is what you wanted, is 1060. You could also do it with Venn diagrams by just sort of playing around with it. They tell you that the whole circle A has 1500 elements in it, so I sort of indicated that as so. But they also tell you that if you take everything in the union of A and B, in other words, that's anything in either or both of those circles, you're supposed to get 2250. Well, just looking at those two numbers, plus the fact that they tell you that the intersection has 310, that means that the overlap is 310, you can easily figure this out now, because if you've got 1500 elements in A and you've already accounted for 310 of them, that must mean that there are 1190 left in A that aren't in the overlap. And also, you need to find that number where the question mark is. That's the number of elements in B, but not in A. How can you figure that out? Well, it says there are 2250 elements in either A or B. So how many are unaccounted for? Well, 1500 of them are in A. That means the rest of them must be inside of B, but not A. So that would fill in the number of elements that are in B and not A. And now the question was, if you go back up to the original question, the question was how many elements are in B? Well, B has the 310 that overlap with A, and then the extra 750 that don't overlap with A. And if you add those two together, you get 1060, which is the same answer you got using the inclusion-exclusion principle. Now you tell me which way is easier. Obviously, the inclusion-exclusion principle is somewhat easier, but you always have the fallback of the Venn diagram if you need it. 25. Use the given information to find the number of elements in each of the regions labeled R1 through R5. They tell you some information. They tell you that the number of elements in A is 29, the number of elements in B is 33, the number of elements in C is 38, the number of elements in the intersection of A and B is 16, the number of elements in the universal set is 78, and they also put some information in the Venn diagram itself. They tell you those numbers 7, 3, and 5, even though they're not listed up there at the top. And they just want you to finish it out. So, as I've said before, it's best to start in the dead center if you can, but 3 is in the dead center, and I already know that. So you want to probably start spiraling out, and you can start where you like, but I decided to start with that football-shaped region, which is the overlap between A and B. So that would be the intersection of A and B. And they tell me that it's 16, but I already have 3 inside that football shape, So that means I have 13 more that I need to put in order to get 16 inside that football shape. So the number of elements in R sub 2 has to be 13. And then you sort of keep going. I know everything inside of circle A except for that R sub 1. So given that, if I add up everything inside of circle A, I just found out that R sub 2 is 13, so it's 13 plus 3 plus 7. The only thing I'm missing is the number of elements in R sub 1 because it told me at the very top that the number of elements in A was 29. So if you look back at the very top, the number of elements in A is 29. So the only thing I don't know is the number of elements in R sub 1. But I will now because all I need to do is subtract 23 from both sides, and it tells me that the number of elements in the R sub 1 region must be 6. So I can put that in there. Then you move to circle B. If you look up top, it says that there are 33 elements inside the circle B. That consists of the number of elements of R2 plus the number of elements in R3 plus the number 3 plus the number 5. And we've already found the number of elements in R sub 2 to be 13. So the only missing thing is the number of elements in R sub 3. If you add 13 and 8, you get 21. If you subtract 21 from both sides, you get 12. So that tells you the number of elements in R sub 3 is 12, so you can plug that in. And then you move to circle C. If you add up all those numbers, you're supposed to get 38. If you look back at the top, the number of elements in C is 38. So if you add up the 7, the 3, the 5, and whatever the elements in R sub 4 is, you get 38. Well, 7 plus 3 plus 5 is 15. If you subtract 15 from both sides, you get the number of elements in R sub 4 is 23. And now you just need to know the R sub 5 region. So you have to look at the entire universal set. And the entire universal set, at the top, it adds up to 78. It says the number of elements in the universal set is 78. So if you add everything up, you get 78. And remember, I already know some of these numbers. I know that R sub 2 is 13 and R sub 3 is 12. So I'm just adding up 6 and 13 and 12 and 15 and 23. And then whatever the number of elements in R sub 5 is, that's got to come out to be 78. It turns out you have to have 9 elements in R sub 5 in order to make all those numbers add up to 78. So the number of elements in R sub 5 is 9. Number 26. In a survey of 600 investors, it was reported that 379 had invested in stocks, 324 had invested in bonds, and 75 had not invested in either stocks or bonds. Question A, how many investors had invested in both stocks and bonds? And B, how many investors had invested only in stocks? Before we get too deeply into this, let's go ahead and put our Venn diagram up. We know that the number of investors, which is 600, is the number of elements in our universal set. If we have a set S for stocks, that would be 379. If we create a circle B for bonds, that'll be 324. And then if you look on your Venn diagram after you draw it out, the 75 are the number that did not invest in either stocks or bonds. So that goes on the outside of both circle S and B. It's the area outside of both circles. Now, that area outside of both circles is 75, but what's the area inside of both circles? Think about that a minute. That's the rest of them. So if I know that there are 600 investors and 75 of them did not invest in either stocks or bonds, if I subtract, it gives me 525. Those are the number of investors who invested in either stocks or bonds. In other words, that's S union B. The union just throws them all together. So 525 investors invested in either stocks or bonds. And that's important. I need that so that I can use the inclusion-exclusion principle. That says that the number of elements in the union of S and B is the number of elements in S plus the number of elements in B minus the number of elements in the intersection of S and B. Because I've counted some twice by counting the number in S and B, I've double counted the number in both, so I subtract off one of my double counts. Once I get that equation, I'm home free because I know 3 out of the 4 values. I just calculated the 525, which is the union of S and B, that number. We were given the number of elements in S as being 379, and the number of elements in B as being 324, and the only unknown is what we're solving for. So if I add 379 and 324, I get 703, and if I manipulate that around, I find out that the number of elements in S union B is 178, and S union B is the set of investors that invested in both, so that is the answer to question A. Moving on to B, think about it a minute. It's asking about stocks. So we know from the top that 379 invested in stocks, but we want to know how many invested only in stocks. We know from part A that 178 invested in both, so if you put that on the Venn diagram, it might help your thinking a little bit. If 379 invested inside the stock circle, but 178 are in the overlap, if you subtract 379 minus 178, you get 201. Those are the people who invested in stocks but not bonds, and that's what question B is asking for. How many investors had invested only in stocks? It's 201. Number 27. During 1 month, the Blood Donation Center found that 45.6% of the donors had the A antigen, 14.9% of the donors had the B antigen, 4.8% of the donors had the A and the B antigen, 84.4% of the donors were Rh positive, 87.9% of the donors had the B antigen or were Rh positive. The question is, in the A part, find the percent of donors that have the A antigen or the B antigen. Again, the inclusion-exclusion principle, as I've said, works with percentages as well. So if I want to know the percent of donors that have the A antigen or the B antigen, I use the union. So the percentage that have the A or the B antigen is the percentage having the A antigen plus the percentage having the B antigen minus the percentage having the A and the B antigen. So the percentage A union B is a percentage A plus a percentage B minus a percentage A intersect B. And I know these numbers, all but the one on the left. The problem told me that the percentage of the donors that had A antigen is 45.6, B antigen is 14.9, and both A and B 4.8. Do the arithmetic and you get 55.7% have the A or the B. The B part, I can also use the inclusion-exclusion principle, but this time I'm looking for the B antigen and Rh positive. So the percentage that have the B antigen or the Rh positive antigen is the percentage having the B antigen plus the percentage having the Rh plus antigen minus the percentage having both. But this time, I know the number on the left. I know that the percentage having the B antigen or the Rh plus antigen is 87.9. It's the last piece of information they gave us in the original problem. I also know that the percent having the B antigen is 14.9. The percent having Rh positive is 84.4. But I don't know that intersection because that's the question I'm trying to answer. So I just add up 14.9 and 84.4 and get 99.3. If I take the negative term to the left and subtract 87.9 from both sides, I end up with the percentage of donors having the B antigen and or Rh positive is 11.4%. Number 28. Given that the set A has 46 elements and the set B has 25 elements, determine each of the following. I want to know the maximum possible number of elements in A union B, the minimum possible number of elements in A union B, the maximum possible number of elements in A intersect B, and the minimum possible number of elements in A intersect B. And here's the way I would look at it. If you're looking at A either intersect or union with B, think about two sets A and B. Suppose they don't intersect at all. And there are 46 elements in set A and 25 elements in set B. That's sort of an extreme case where they don't overlap. And then start pushing them together. Suppose you push them together so that there's one overlap. notice that the 46 goes down to a 45 and the 25 goes down to the 24. The reason is because there's one in the middle that's a part of both. You start letting them intersect. What if you push them a little closer and have 2 in the middle? Now the 45 goes down to a 44 and the 24 goes down to a 23, and there are 2 overlap. You still have 44 plus 2 is 46 if you go back to the top, and 2 plus 23 is 25 so if you go back to the top. You're just pushing the circles closer and closer together, and if you keep pushing them enough, finally the smaller circle goes completely inside and is swallowed by the bigger circle. In this case, A was 46 and B is 25, so the B set, the smaller one, just completely, you keep pushing, will completely go inside the set A. So the Venn diagram at the top is sort of one extreme, and the Venn diagram at the bottom is kind of the other extreme. Now, if you look at that, I think you can answer each of these questions. So let's go back to the question about the maximum possible number of elements in A union B. Well, A union B, notice that there are 40, in the top one there are 46 and 25, that's 71. If you count them anywhere else, it's never going to be that big. If you go to the second Venn diagram and add up 45 and 1 and 24, you only get 70. If you go to the next one down and add 44 and 2 and 23, you only get 69. And finally, by the time you get to the point where the big circle has completely swallowed the small circle, you only have 21 plus 25, you only have 46. So if I'm looking at A and I'm looking for the maximum possible number of elements in A union B, it's obviously going to be 71. 71 is the biggest possibility. And you can see now that it happens when the two sets don't overlap at all. So anytime you answer the question about the maximum union, it's going to be just add up the two sets of elements in each one. It'll never be any bigger than that. Well, what about the minimum number of elements in the union? Well, you can see that's going to be at the bottom. When B gets completely swallowed by A, you only have 21 plus 45, you have 46. That's the smallest it can be. So in general, when you're doing maximum union, it's just adding the two numbers together, the two element numbers together. When you're doing the minimum union, you pick the bigger one because it's completely swallowed the smaller one and you're only left with the 46. What about intersection? Intersection is overlap. You can see the biggest overlap is at the bottom, and that's when all the elements of B go into side of A, and the answer would be 25. And the minimum number of elements in the intersection is up top. There's nothing. There's no overlap, and it would be 0. So however much trouble you had getting through this, it's easy to see after you've done it how it's going to work. The answer to A, which is the maximum union, is always just going to be the sum, 46 plus 25, or whatever those numbers happen to be. The minimum union will always just be the bigger number, so 46 in this case. The maximum intersection will always be the smaller number, which in this case is a 25, and the minimum intersection will always be 0. Number 29, determine whether the sentence is a statement. X squared is equal to 16. I've said before, and I'll pull up the slide, these open statements, these statements that turn out to be, in this case, equations with variables in them, are statements. They're just called open statements because the truth or falsity of them depend on which value you put in for X. But nevertheless, it is a statement. And again, same thing. These are open statements, which means they're statements. The truth or falseness of them depend on what value you choose for X, but nevertheless, they are statements. 31. Write the symbolic statement in words. P is the tour goes to Italy. Q is the tour goes to Spain. R is we go to Venice. S is we go to Florence. T is the hotel fees are included. U is the meals are not included. And we want to write in words, R implies not S. Remember, implication is really if-then. So another way of saying that is if R, then not S. So if you're looking at that, if we go to Venice, because R is we go to Venice, then what? It's the negation of S. S is we go to Florence. So the negation is we don't go to Florence. So it would be if we go to Venice, then we do not go to Florence. It's the first choice. 32. Write the symbolic statement as an English sentence. P is Taylor Swift is a singer. Q is Taylor Swift is not a songwriter. R is Taylor Swift is an actress. S is Taylor Swift plays the piano. T is Taylor Swift does not play the guitar. And we want to translate the statement S and not Q implies T. So it's an implication, so it's an if-then. S is the statement Taylor Swift plays the piano. There's a symbol for and then not Q. Q is Taylor Swift is not a songwriter, so that would be Taylor Swift is a songwriter. So if Taylor Swift plays the piano and she is a songwriter, then T, which is Taylor Swift does not play the guitar, and that happens to be the first selection as well. 33. Write the sentence in symbolic form. P is Stephen Curry is a football player. Q is Stephen Curry is a basketball player. R is Stephen Curry is a rock star. S is Stephen Curry plays for the Warriors. And the sentence we want to put back in symbolic form is Stephen Curry is a rock star, comma, and he is not a basketball player or a football player. Now remember that comma is important. We use the comma to help us with grouping so that everything on the same side of the comma gets grouped together. So Stephen Curry is a rock star is on the left of the comma, and that's the statement R. And is the connector we're using. He is not a basketball player. Q says he is a basketball player, so that's going to be a not eventually. P is Stephen Curry is a football player. And we're doing an or. And remember, the grouping symbol says that we want to group everything to the right, or at least on the same side, in this case the right of the comma, together. And don't forget the negation. The negation says to make that a not, Q or P. So you can see Stephen Curry's a rock star is R. He's a basketball player is Q. He's a football player is P. There's an or there, and since both the Q and the P are on the same side of the comma, they're grouped together, and then the negation is thrown in there to make that a tilde. And that happens to be the second choice. 34. Determine whether the statement is true or false. 5 is an odd number or 5 is an even number. Okay, 5 is an odd number, that's true. Or 5 is an even number, that's false. True or false. Remember, or is only false if both are false. Well, they're not both false, so it would be true. 35. Translate the mathematical statement into symbolic form. Any angle inscribed in a semicircle is a right angle. We're going to use I for an angle inscribed in a semicircle, and we're going to use R for an angle as a right angle. Remember, when we have problems like this, we want to translate them into an equivalent if-then form. So, how would you do that? It's got to mean the same thing. Any angle inscribed in a semicircle as right angle is the same as saying if an angle is inscribed in a semicircle, then it's a right angle. We've talked about that in class and in homework. I'm not going to belabor it again, but you have to be at the point where you can read that first sentence and translate it correctly into an implication. Once you do that, you're home free, because an angle inscribed in a semicircle is what we call I, and it's a right angle is what we're calling R, so it would be the fourth choice. I implies R.